Okay, let's discuss the solution to this problem. Again, we've got a bird, half-kilogram mass, that's flying on a path from a building ledge to the ground, and the question is how much work does the gravitational force, or the weight force, do on the bird during the flight? And we're going to use this formula that we just gave. It's really a definition. We've got to sort of warm up to it a little bit, but let's work with it. Here we need to get x and y components, so of course the first thing we need is a coordinate system. So let's decide on a coordinate system. Here, since we're given vertical and horizontal displacements, we may as well choose x and y to be vertical and horizontal. And let's calculate the work done by gravity on the bird using this formula. And in this case, the gravitational force I've got to remember is straight down. So that means Fy is negative and Fx is 0. So when I put that in, we see the 30 meters horizontal displacement doesn't really come to anything because it's multiplied by a 0 x component of the weight force. And the y component of the weight force is negative, and it has magnitude mg. Okay, so that's my Fy. It's a negative force y component because it's going down and plus y is up. And finally, my y displacement is also negative because we're going from a higher y to a lower y. So the displacement y component is minus 50 meters. Crunch that stuff in your calculator and you'll get 245 joules. So that's the answer to problem 1. Now, let's go on and try to simplify the formula a little bit, and maybe you've seen a form like this in the book. Oftentimes, people try to simplify that formula by choosing their axes so that the object is displaced only along the x direction. So here we've taken the direction of the displacement in between initial and final, and we've lined up with x-axis with that and make the y-axis perpendicular to it. And then when we go back to this formula, it simplifies a little bit because the y displacement component is now 0, just because I've chosen a good coordinate system. And therefore I can forget about that second term and just use fx times delta x. Okay, so in this way of thinking about it, if you know the displacement of the object, the fx represents the force component along the direction of displacement, and the delta x represents the displacement magnitude of the point at which the force is applied, which is, in this case, just the motion of the whole object. Now, a common case that you'll find in textbook problems are imagine that you're dragging a box along the ground. So you're dragging it by a string, and the string is tilted up at some angle theta to the horizontal. So we're dragging this box from an initial position to a final position by keeping a constant tension in the string at a constant angle to the ground. And in this case, we can use that formula. The work is equal to fx times delta x. Delta x just represents how far we've moved in this direction, and fx represents the component of the force along that direction of motion. So we need the horizontal component of this force. That's just f times cosine of theta. So f times cosine of theta times delta x is one particular way you might calculate fx if you know that angle, theta. Now, let's go on and do exercise 2 on the same worksheet, the worksheet. Here's what at least the setup is and the first part of it. We've got a 2-kilogram block being dragged. Hey, that sounds familiar. A distance of 2.5 meters along a table at a constant velocity by a string with a 50 Newton tension force in it, directed at an angle of 20 degrees above the horizontal, and we keep that magnitude and direction angle for the entire motion from the initial state to the final state. In the first question, you're going to do all of the parts to question 2. The first question is, how much work does the string force do on the block during this motion? Okay, so let's take a break and you work on that.